Hi guys, welcome to another lecture number 9 of our series of lectures on model-driven engineering and model-assisted software development. So it is likely this will be the last lecture. I'm not entirely sure if we have enough time to cover all the material, so we'll try our best. Before we proceed, let's just review quickly the path that's taken us thus far over this number of lectures. This is not quite the path that I've introduced in the lectures themselves, but the path that I've taken to get to the creation of Mast. I didn't really want to create a new methodology as such. I just wanted to find good theoretical foundations for my tool Dogen. And because of that, and because of the research I did on the field of model driven engineering, my conclusion was that a new methodology was required. So let's just review quickly how we got to that conclusion. So the first thing I did was I took the path of independent rediscovery. That is, I had no idea that model-driven engineering existed, and as part of a code generation team, I just created a code generator without any idea of the theory. Once I gone past that, I then spent some time going through the body of knowledge of model-driven engineering. I mean, part of it was actually just the conceptual leap that was required in order to understand that MD was not a methodology, but actually a body of knowledge. So that was part of the journey that I took. Then the next step, once I understood what MD was all about, the obvious question was why did I not know of this before? Why isn't everyone using this? So I spent a lot of time going through the literature trying to understand who was using MDE and what happened in terms of those experiences. What were the difficulties? What were the problems, and so on. Once I'd done that, I then spent some time trying to understand what tools were there that were using code generation, either with the knowledge of the existence of MDE or even without the knowledge, and but they were popular with software developers. The reason why I wanted to do that is because I wanted to understand what are the characteristics of those tools that developers find useful, and how do we ensure that whatever tool we come up with the MDE approach, that it still shares the commonalities with those tools. And finally, this is the step we're currently in. I took all this information together and used it to outline a new approach. Um, so that new approach is called MASD, Model Assisted Software Development. And what MASD is a f- a s- the dressing up of AC, architecture centric, model driven software development, which is could be replaced with MDE really. Just historically, ACMDSD was the name of this approach. But it was the taking of the ACMDSD approach and the dressing up, the conversion of that approach into a methodology. And taking into account all of the requirements that we've outlined so far. Um, if you remember, we covered that in the previous lecture. Um, and a methodology is composed of three elements, as we discussed before. It needs to have some kind of overarching philosophy. That's sort of the philosophical approach to the reason why you're doing it. It needs to have a set of processes and actors. Um, and the processes and actors, these are who does what when. So the processes focus on the actual activities, and the actors focus on the who, the persons their responsibilities. And we also need the modeling language. By modeling language, what we mean is a set of terms, a language really that people using the methodology agree with. So with these three components, it's possible to then all these three components put together form a methodology. Now, in terms of driving this philosophy, I decided to separate the philosophy into two components: a vision and a mission statement. But before we go into that, let me just explain why it is important, why it is so important that we create a methodology rather than just add to the model-driven engineering body of knowledge. One of the problems we found with adoption is um, it is very difficult to even begin to understand what model driven engineering is. So, for an average software developer like myself, it was very difficult to get to grips with it. And what developers, the adoption research revealed, what developers really want is a tool they can start to play with almost immediately, with very limited knowledge of the theoretical background. And what they want to do is they want to grow their knowledge over time without having to take lots and lots of time just to understand how things work. This is how we normally apply new things. This is how we got involved with things like protobufs and other technologies. We take some example from the internet, for instance. We run protobufs, we generate some code, we get the gist of it, we apply it to some problem, and then we increase our knowledge of the specific technology over time, slowly and incrementally. We don't just take 6 months out like we had to do with Dogen to understand the ins and outs of a given technology. We experiment with it, and that's how we build our knowledge. That's how normal software engineers think. So therefore, the reason why we moved away from just saying to people, just use the MD body of knowledge, and towards a methodology, a very self-contained, encapsulated methodology, was because that's more in line with the approach of how normal software engineers think. So, in order to create this philosophy, as I mentioned before, we divided the methodology or the philosophy into two components: the vision and the mission statement. So, the vision is to accelerate MD adoption by traditional software engineers for the generation of infrastructural code. The vision is trying to set something far in the future. It's not really something that you address immediately. It just sets the overarching idea of where you're trying to get to. So in an ideal world, we would accelerate MD adoption by the typical software engineers, and we want to specify exactly what we want to use MDE for, because in theory you could use MDE for everything, and we've seen this with case, and we've seen this with the MD body of knowledge. So instead of creating a very ambitious target, we flip it the other way around. We focus on a very simplistic target, something that's achievable, and something that's easy to explain to any software engineer, because we all know what infrastructural code looks like, even if you can't describe it by formal means. The mission statement focuses more a bit on the concrete steps that are required in order to get to the vision. So, as we mentioned before, Stahl and Volter's book, when they describe ACM DSD, their focus was on this separation of code into three different kinds of code. Um, and the code they're specifically interested in is the schematic and repetitive code. The schematic and repetitive code, again, it is very difficult to formally describe what it is, and we will explain later how we got around that lack of formality. But for now, let's just assume that we all understand in a software project there is this element of SRCs, schematic repetitive code. Now, in MASD, we decided to slightly abstract ourselves from the notion of code, because we're not just interested in source code, we're interested in any infrastructural pattern that's schematic and repetitive. So, in that sense, we don't really care just about files, but we also care about directories and anything else. I mean, we haven't quite gotten to um, any additional element that displays this SRPPs, as we now call them. For now, it's only files and directories, but the abstract notion allows us to, in the future, identify additional patterns. So the fundamental mission is to manage the life cycle of these SRPPs. And what we mean by the life cycle? Well, we mean the identification of the patterns, the capture of those patterns, and the classification of the patterns in an open, centralized, and continuously evolving library. So we want to take patterns on, we want to perform a taxonomical exercise on those patterns, and we want to integrate those patterns into the library, well identified and defined. And then we want to also create an analysis. We want to also analyze the patterns, and we want to characterize the dependencies between patterns, as well as their variability requirements. And what we mean by that? We mean that it's often the case that when we identify a pattern, that pattern has a relationship with another pattern. Let's take this from the abstract world into a slightly more concrete world. Let's imagine that one of the patterns that you identify is serialization. Let's say, for example, serialization into XML. Um, Another pattern that will almost obviously will be identified is a type definition. So when you create a class, if you can somehow extract all of the structural components of that class, um, we would consider that definition as one of the patterns we can identify and classify. But the serialization pattern uh, will then become dependent on the type pattern, because depending on the structural definition of the type, the serialization pattern will vary. That's why there's a dependency between these two patterns that we've identified. In addition to this interdependency, there are also variability requirements. So, for instance, in the type pattern, we can define multiple components of that pattern, such as a constructor, um, maybe a toString method. There will be lots and lots of different knobs that we can switch on or off, and those knobs will make part of the variability requirements of the pattern. Those must also be part of the analysis that we perform for each SRPP. And of course, the whole point of this exercise is to generate these patterns. So we want to regenerate the pattern by automated means. Once we are generating, we want to enforce some kind of conformance or compliance testing in order to make sure that once the pattern has been absorbed into the library, we can guarantee that we always generate the pattern correctly. Afraid my dog's shouting a little bit. Um, And of course, we need to worry about the evolution of the pattern, because the pattern is not static. We don't just create a type definition, for example, and it's frozen in time. We are going to get more and more samples, and we will want to increase the variability. We want to change some aspects of the pattern. So the evolution of the pattern is very important. And eventually, as we are life cycling the pattern, eventually the decommissioning of the pattern will also be relevant, because over time, as we start to accumulate patterns, eventually we will not need certain patterns. So that's kind of the mission statement. We want to focus on schematic and repetitive patterns, which is fundamentally what underlies ACM DST, and we want to manage the life cycle of those patterns. Now, the mission statement and the vision are important in order to define the philosophy, but we thought that was actually not sufficient, because if you go back to our requirements, uh, not everything was captured by the mission statement and the vision. So we needed to create a set of principles that we can explain to anyone using this methodology that will help you navigate what it is that we're trying to do. And we came up with 6 principles that we think uh, capture well, the core ideas around MASD. And so we'll cover these now. So the first principle is we want a narrow focus. Narrow focus is very important. We already have the broad focus of the MD body of knowledge that is applicable to pretty much any domain and enables you to do pretty much anything in the space of model-driven engineering. So there is no need to create another methodology that takes on those goals. We've already tried that before with the MD variants such as MDA and even further back with case. So now we have to move, have to shift towards the other side of the spectrum. MAS is a very narrow focus. It only cares about infrastructural code and nothing else. MAS also attempts to integrate pervasively. What we mean by that is, in the past, according to our research and adoption studies, on adoption literature, in the past there was an attempt to create model-driven engineering tools that focused on modeling and on tool development from the perspective of the tool developer. Now, what we found out with our research on special purpose code generators is that that's not what develop and also in MD adoption, that's not what developers want. What developers want is tools that are very, very similar to the tools they use already. So from the perspective of code generation, one of the reasons why the special purpose code generators were popular, in our opinion, was because they looked very much like compilers. And because of that, they integrated into the workflow of developers. So they didn't have to change their build tools. They didn't have to change anything in terms of their build process. Well, they had to change very slightly the build process. So it's very important to integrate pervasively with the existing development environments. Um, we also need to evolve gradually. By that we mean is it's important to take on more and more of the scope of the infrastructural problem domain, but at the same time, must make sure that that evolution is gradual. If we must make sure that we keep supporting existing use cases and we keep expanding towards the problem domain that users find significant, instead of just taking on everything just because it's related to infrastructure. So evolution is important, but a gradual evolution is also very important. Um, the other lesson we learned from NDA is that it's important to create an open governance process. So NDA did have an open governance process, but because it was based on standards and standards organizations, and it was a process that was too cumbersome and too slow for the average developer. Um, so instead, we proposed that the process is for governance is much more akin to a regular open source project, enable anyone that is interested to contribute. Um, and this takes us to the next point, which is MDA taught us that standards are really important, but we don't really want to ossify the approach. The problem with the standards used in model-driven engineering via MDA was that those standards take a very long time to define, and the purpose of the standards, which was to create interoperability between tooling, never really materialized. So instead of going for formal standardization, what we try instead is to use informal, de facto standardization. And we enforce standardization via creating a single tool that embodies the methodology. And that is effectively the standards. And if other people would like to participate on MASD, we request that they follow the approach of the single tool. As we shall see, this is called the MAS reference implementation. And finally, and the main reason why MAS is called model assisted software development, is the role of MAS is to assist and guide. This is a bit different from, say, the model driven approach. We don't want models to drive the software development process. We want users to still drive the development process by whatever means they are driving it at present, whether it's domain driven, whether it's test driven. For us, we don't really impose any changes at that level. I'm afraid I have to pause for a second. Too many distractions in this place. So as I was saying, the point of MASD is to assist and guide. So we don't want to take over the development process, just like I don't know, using Clang does not take over your development process. We want to provide you with a tool and an associated methodology that comes with that tool. But our role is to assist and guide, um, and we shall see why assisting and guiding is important. Because just like, say for example, with Clang, um, the basic use case of Clang is just to use Clang to compile your code, your C++ code. But Clang offers you a road that you can go in, creating tools, for example, using the Clang code base. So this is not necessarily the most common use case for Clang, but it's available to users. And in our approach is similar to that. We will offer you a base case, which may be very, very simplistic, which may be just kind of like protobufs, I guess, with a bit more coverage. But then ideally you should move over in a set of levels, um, getting closer and closer to the MDE vision. Now you're not going to achieve the MDE vision using MASD, because we don't really provide you with the tools necessary to do model driven engineering. We stop short of that, but we will climb a ladder that will take you closer to that approach. That's the role of MASD. And then eventually you will, if you want to keep going in that direction, eventually will move towards a proper MD approach. And at that point, you need to use MD tools such as EMF, which you then can integrate via the integrate perversely with MASD. Um, so in terms of, as I mentioned before, one of the components of the methodology are the processes and actors. So as I said, one of the inspirations for our approach is the open source, free and open source software uh, world. And because of that, we designed MASD very much to follow the same structure. MASD is sort of an echo of an open source project. Um, so within MAS, there are three actors: the maintainer, which is myself at the moment, but ideally this should really be a group of people, the developer, and the user. So the MAS maintainer, the role of the MAS maintainer really is to keep the different aspects of MAS is the final arbiter of all the different aspects of Mast. And we shall see in a second when we talk about processes what these aspects are. So, for instance, if we'd like to make some fundamental changes to the methodology, the maintainer is responsible for defining whether those changes are acceptable or not. The maintainer also is responsible for accepting changes from external developers, which will propose changes to different aspects of Mast. Um, and the developer is somebody who wants to make fundamental changes to Mast, but is not necessarily, it doesn't have any special rights, such as the maintainer. So the developer is there to propose changes, but it doesn't have the ability to enforce those changes like the maintainer does. And finally, we have the user of Mast, which is the end user, a regular software engineer. This will become a bit clearer when we talk about the processes. So there are three components to Mast that are important. The Mast reference implementation, which is Dogen, the Mast software specification, which is what the thesis in effect is. Um, and the idea there is that we specify a high level what the Mast methodology is, and in other words, all the concepts that we've discussed so far. Um, and then we have a combined set of products that are the Mast product reference implementation, which we don't mention here in the process. Those products are used to give you an example of what Mast is all about, and they're also a way to test the compliance of Mast. Now, in order to maintain those three components, we have a set of processes. So the first process is the MRI development process. This really is the most important process of all the processes. And in other words, this is just the software development of Dogen. Uh, the MRI development is just like any other software product. We just have pull requests. You can come in and propose changes and so on. The MSS software development, also the MSS development, is the management of the documents related to the specification of Mast. This is not really expected to change very often. And in fact, I think the thesis will probably be the canonical specification for Mast. I expect maybe a few minor changes, but not huge amounts. The reason why I say that is because the philosophy of Mast, which is what we specify in the thesis, um, it's defined as a whole, and I can imagine that there will be tweaks that are required. But if you want to fundamentally change the philosophy, I think you are creating a different approach, and I suspect if that's the case, that approach should have a separate name and it should go elsewhere. So I don't envision any major specification changes to Mast. However, I expect there to be very minor tweaks. And one of the ways in which we try to ensure this is the thesis is written by example. It tries to demonstrate the approach that we've done so far, and it explains the direction in which we're going to go. But it doesn't try to specify too much. It just it is an empirical demonstration of how MASD is applied to itself. And that is done so that we don't have to be changing the specification every 5 minutes as we increase our understanding of the problem domain. So the MSS development process is something that is expected to happen very infrequently. The key thing really is the MRI development process. And closely connected to the MRI is the MASD application process. Now, the application process is basically when the user takes our tool, the MRI, which is just Dogen, and applies that to their own software program. Um, in general, the users are probably just going to use the tool out of the box. But of course, there will be limitations to the tool. And because of that, as part of the MRI development process, we cater for um, shortcomings in the MASD application process that will then require changes to the MRI. Um, and these two processes are going to work in tandem. They work together, really. Um, and finally, we have the Mast composite process. Now, the Mast composite process is probably the most important process in the sense that that's how we got this far. The reason why that is because we combined the application of Mast to the development of Mast. We locked these two things together. And this was done on purpose and by design. What I mean by that is, to develop Dogen, we used Dogen, and Dogen was the source of MASD. And this is very important because we could have, there's nothing stopping us from developing a real application. And in fact, that's exactly how I started when I was working on code generation team. We had a real trading pricing system that we were developing, and we also had the domain architecture. And we separated these two roles, and they worked in tandem via the dual tracks, the dual track approach that I described a few lectures before. However, there are reasons why this is not ideal. The first reason is, if you're developing by yourself, you now have to divide one developer into two different applications, and you have this shared focus where you're trying to focus on the end application, let's call it, and you're also focusing on the domain architecture, and your energy is split between these two. And so what will happen is you will spend half of your time developing the application, then you're going to bump into a shortcoming of the domain driven approach. Then you will have to take that hat off and go back to the MRI, the development of the model driven engineering tools. Then you'll spend some time working on that, and then eventually you'll finish that feature, and then you'll supply that feature to the team that's doing the application. But because there is no team, there's only yourself, you then have to go and put back the hat of the application on, and then develop the application. Now, this could work in a team of 10 people or more, like we had in a real financial world, but it doesn't work in a team of one because you spend all your time context switching between these two worlds. So, if you think about it, and we've spent a lot of time thinking about this, the limit of this function is to have a single application that enables you to instantiate both the application process as well as the MRI development process. That is the ideal scenario. And it is actually quite possible because if you think about it, Dogen is a very complex application. It's very large and it's a significant application. So therefore, it makes perfect sense to combine the application of Dogen with the development of Dogen such that you create a single loop that's very, very rapid. Um, and in that way, you don't have to context switch as much. Now, in practice, if you follow Dogen development, you notice that we did have to context switch because what tends to happen is you're working on a feature of Dogen, and then you find the limitation of Dogen while working on that feature, and then you stop that development of the feature for a little while. You think about the fundamentals of what it is that you're trying to do. You then go on a tangent developing architectural infrastructure in order to support that feature, and then you finish that, and then you have to go back. And this happens throughout the entire life cycle of Dogen, but it's still much better than having to context switch problem domains. So that's why the Mast composite process is very, very important. Um, Now let's think. Let's talk about a little bit more about the domain architecture. How is Mast? What is the domain architecture of Mast? So we came up with three domains that we consider to be the fundamental domains of Mast. So there's the physical domain, there's the logical domain, and there's the variability domain. The physical domain is composed of a set of physical artifacts, such as files and directories. Like I said, we want SRPPs to be an abstraction of physical concepts, but in practice, we only found two items, which are files and directories in the physical domain. Perhaps there will be others, but that's as far as we got. Then there's the logical domain, which is once you've analyzed a set of files and a set of directories, you're going to come up with some logical constructs that represent those entities, and you're going to place those in the logical domain. And finally, we have the variability domain. And the idea of the variability domain is um, over time, you're going to build more functionality, more optionality in terms of um, the entities that you observe in the logical domain. And that optionality, that functionality that is configurable, needs to live inside of the variability realm. And that's why we need the variability domain. These three domains put together form what Mast calls the logical physical space, or the LPS. The three entities, the three domains work together. There is none of these entities should be considered in separation. They exist in this space. We shall see later on why we think this is important. So as an example, we're getting closer to the implementation now. The, the way things work inside of Mast is we start off with some very simplified representation of an entity, uh, and this is so that we can support multiple inputs. So, for example, an input could be UML diagram, an input could be um, uh, any other form, XMI, um, any form that enables you to transport structural information. And the codec is this simplified input that enables you to parse multiple inputs. And then we convert that representation over to the logical model, and which are the entities that we discussed a second ago. And those entities can then be projected across the space over to different physical representations in a physical model. Um, so, for instance, it could be a type definition, it could be a serialization over to XML, it could be serialization over to JSON, and so on. And eventually, we will take that representation and we will output that over to a file in the file system or a directory in the file system. And that's kind of the projection across spaces that we envision. Now, this gives you the impression that we start off from this logical representation, but actually MASD starts off from this side, which is a bit different from how um, the world works in model-driven engineering. So if we take the typical analysis and design that happens in model-driven engineering, what tends to happen is you observe the problem domain and you create a logical representation of that problem domain. So for instance, let's say you're working on the financial domain. The first thing you'll do is you sit down with a trader, for instance, and you'd say, what kind of products do you trade? And the trader will say something like, well, we trade FX spot, we trade bonds, we trade, I don't know, any number of financial products. And then you're going to construct a logical representation of those products inside of your logical domain. Eventually, that logical representation is going to be refined via cascading over to a physical representation, which will be composed of classes and files and things. Well, actually, we could be composed of files and directories. Um, and that's the typical workflow inside of model-driven engineering. With Mast, we start the other way around. We start by analyzing a set of files and directories, and we look for patterns in those files and directories, and we abstract those patterns over to a logical representation. Well, actually, we extract those patterns first to a physical representation, and then from the physical representation, we move to a logical representation, and potentially that logical representation could have multiple levels. Um, and and that's completely separate from the problem domain, um, the application problem domain, which has no relevance for MASD, other than supplying us with samples in the physical level. So we don't. MASD is completely agnostic to finance or whatever problem domain you're interested in. We only care about patterns that are observed in files. That's our problem domain. So this makes the physical analysis and design a little bit different because we're not going to go to a domain expert. We're going to go to physical instances. Um, and so the core entities that you see in MAST are going to be these ones. They're going to be artifacts, and they could be file or folder artifacts. And within a file artifact, we can have different kinds of files. Now, for now, we're not particularly interested in binary files, so we excluded those from MAST for now. Um, that's just for practical reasons. We haven't found any examples that are useful to us. But we have found a lot of text file artifacts, as you'd expect. And the job of our analysis is going to be to create a taxonomy and a morphology of these file artifacts, including subdividing these file artifacts into segments. And part of that taxonomic work is also to classify those file artifacts into technical spaces. And now you understand why it was so important for us to talk about technical spaces and platforms, because the morphology and the taxonomy are going to be, platforms and technical spaces are key elements in the morphology and taxonomy, mainly the taxonomy of files and directories. Um, so, as we described before, there is this distinction in man's world between the physical domain and the actual file system. Um, this is a bit confusing. It took me quite a while to work this out. Um, just because Mast contains a model of physical entities, that does not mean that these physical entities are actually in their physical form. So, in other words, it's perfectly possible for us to model a physical entity in a logical representation. That is not the actual physical entity, it is just the logical representation of the physical entity. So, in practice, this is really not that relevant because we don't really spend a lot of time distinguishing between the modeling of physical entities versus the instance of the physical entity. But it's important to get this point across because otherwise you may confuse the file with the MASD entity representing the file. The best way to think about this is to think about it in terms of models and meta models and instances. So a file is an instance from a MASD perspective. Um, the representation of the file within the physical domain is akin to moving up to the model. So it's no longer the instance, but it's the model of the instance. And conceptually, you can imagine there will be a meta model of that instance. And so that's the hierarchical representation within the physical domain. That is completely separate from the logical domain. So in the logical domain, you would have entities such as, for example, class and other entities we'll introduce in a second. And those entities will then project across the physical space into an instance of that class. And that instance of that class will exist inside of a facet, as we will describe in a moment. We are still within the logical representation of the entity. It's only when we write that logical representation over to a file or to a directory that we enter the actual physical representation. For all intents and purposes, we can ignore the physical representation because most of the time we're living in this space, which is the LPS. So we don't really care about that. But just so you understand that when we talk about the physical domain, we're not talking about the files and directories in your file system. We're talking about a model of those files and directories. This is important to understand. So what do we mean by the taxonomy? So what we did is we spent a lot of time going through lots and lots and lots of files and lots of directories, and we tried to classify them. And the main classification we came up with was something like this. This is an example rather than an actual classification. So I'll start here with something that a developer should understand, and then we move our way upwards. So if you take the type definition, you can imagine that the type definition is a trivial function of structural variability. What do I mean by that? I mean that you can imagine that a structural diagram, such as a class diagram, can define the structure of a class. And the file that you see with that type definition is actually a very simple mapping between the structural definition that you see in a UML diagram. It is almost a one-to-one mapping with a little bit of lookups, perhaps, for type definitions and for syntactical sugar. So this is what we call a trivial function, because by trivial we mean that it's very easy to describe the mapping that's happening between the structural definition and the instance of the structural definition that you're seeing there. And types of class definitions we've observed are things like classes, enumerations, and so on. Now, there are other kinds of of trivial functions of structural variability. These are what we call trivial behaviors. So, in other words, they are not just an echoing of the type definition, but they provide some kind of behavior. However, the behavior is very, very simple. It's very easy to define what this behavior is. By simple, what we mean is you can easily conceive a very small set of rules that can encompass the whole of the behavior. So, examples: pretty printing, so a toString method. Pretty printing is a very trivial function of structural variability because you will just iterate or loop through the members of a class, and for each member, you're going to print out the contents of that member. And if the class is composed of another class, well, you're just simply going to call that toString or the pretty printing method, and you recurse that until the object graph is exhausted. So it's very trivial to create a pretty printing function once you've got a structural representation of a class. Similarly, serialization is also another function of structure that is fairly trivial. I mean, you can't call this structural because it is a kind of a behavior. So you can say toXML. So that's kind of a behavior you're adding to a class. But it's not a complex behavior such as compute the valuation of a set of financial instruments. It's quite trivial and it's infrastructural. and so on. So you can imagine that we went through projects and we identified very large number of these trivial behaviors, and we classified these behaviors. Um, and here we just see these examples of these behaviors. So, for example, there's different forms of text serialization, such as JSON, XML. There's different forms of binary serialization, such as ASN1. Um, However, you can imagine that opposed to this structural variability, um, there is non-structural variability. Um, so by non-structural variability, what we mean is, and now remember, we have to put our hat on of we're looking at sets of files. We're looking at very large sets of files, and we're trying to observe what we see. We're trying to classify what we see in those sets of files. We see that in a second. So non-structural variability is more to do with configuration rather than the structure of classes. And for that, we see things such as boilerplate. All files have got lots of boilerplate. Things such as a license and so on. And those are elements that we can classify according to non-structural variability, because you can decide whether you want to emit the license or not. You want to configure the boilerplate in some ways, and we'll see this in a second, and so on. All of these are come under the input variability. And if you remember, we spent some time talking about the taxonomy of variability itself, and now it's coming in quite handy because it is underpinning all of this taxonomy that we're doing here. Um, of course, there are things in the world that are not functions of input variability, and those things we just call complex functions of input variability. So, in other words, we are trying to represent some kind of structure that is so complicated that uh, you can't just create a simple mapping. And for those, we just ignore MASD. We just don't care about those things. And of course, there is not just the notion of input variability. You could just have, I don't know, say for example, free text. That can't be classified as a complex function of input variability. So we call that just independent of input variability, just an element that exists in a project in a file, and there's nothing we can say about it. It's just outside the scope of our um, project. So then we enter this notion of physical modeling processes. As I said, the initial starting point of MAS is to observe a number of files, and then to come up with the morphological and taxonomical analysis of those files. So the process by which we do that is called the physical modeling process, and we took this process from computational neuroscience actually, where similar ideas are applied to the modeling of neurons. And so, what is the physical modeling process? So first we sample. In other words, we come up with a number of files, and we decide which files are part of our sample and which files are not. Then in that sample, we start to decompose or segment the file. We start to observe the different components in that file. And once we observe those components, we give them names and we classify them according to the existent library of components. And then we try to take those constructs and we try to recreate the file. And finally, once we successfully recreate the file, we deal with the catalog of patterns and the variability constraints of that catalog, the parameterization. And for every pattern, we go through this process. What does that mean in practice? So in practice, you have something like this. You start off with a file, and you start to observe the meaning, the semantics of the characters you see in the file. Now, you may think, what do I mean by the semantics? Don't I just mean we're programming, so therefore the semantics are the language or the object model, the object orientation of that language? Actually, that is a logical representation of the entities that you've got. We don't particularly care about that. Now, that might sound a bit extreme because if you think about it, what's inside of the file has to be related to this logical representation. Otherwise, your file would not compile. It would not be according to the syntax of the language. In other words, your file has to be an instance of the language's meta model, because that is by definition what it means to program in a language. But if you take your hat off, your programmer hat off, and you just imagine that you're a person that has never heard of programming, and all you've done is somebody's given you a whole load of text files, and you're trying to make sense of those text files, not even knowing that the notion of programming exists. You don't even know the Kova compiler. You know nothing about those things, and you start to observe patterns. And your job is to then classify those patterns. That's kind of how we do a physical modeling process. So we start to observe the patterns, and some of the patterns we see is we see things such as fields, and if you use Emacs or VI, you know what I mean. These are things that are used to configure the behavior of Emacs and VI, and those fields are part of a mode line because Emacs and VI use that mode line. You also start to see things like a copyright attribution, and you see a short form license. And you notice that all of these things here tend to make up um, something that happens in every file, which we call the prologue, according to the analysis that we've done on special purpose code generators. And similarly, there tends to be an epilogue. So the prologue contains all of this infrastructure, including the decoration, including the header guards. Um, and the reason why we separate the prologue as an entity in its own right, from a morphology perspective, is um, any file that you've got in a C++ project is probably going to have something like this. Um, and even more, any file in perhaps a C# project will also have something very similar to this. Maybe it's not going to have a header guard, but it will have the decoration, for example. And so you can imagine that even though you're straddling technical spaces, you're going through like C++, C#, Java, the concepts around decoration and boilerplate will remain. So these constructs, they are a higher level construct that is separate from the logical construct of, say, a class, and is also separate from a plain file with just text characters. You start to see some kind of topology emerging inside of a file, which is what we see here. Um, in addition, we also observe things such as namespaces, and we all observe that namespaces have a beginning and an end, just like the prologue has a beginning and an end. So here is what the topology is emerging in the morphology. The file is not flat. There's a landscape to the file with rises. For example, we enter the boilerplate that raises the level, and then we start to put things in the boilerplate, and then we lower the level again. So you can imagine that we are visualizing a terrain with topology. And then in that terrain, we then start to observe entities. Now, remember that we don't particularly care about the meaning of these things. So, for instance, we are not trying to say what are all the possible ways in which you can declare a namespace in C++. That's not the objective of this exercise. We're doing it the other way around. We're saying, given our sample set, what are all the possible instances that we've seen of this element, which we choose to call namespace, because that's what the name we see here. And that sample set is going to be very, very small compared to the possible things that you can do with the namespace in C++. Um, and where variability comes in is when you observe this element, which we could choose to call namespace, but eventually we'll abstract that to become something higher level, so that we can use the same concept in other languages, such as, for example, Rust or Java or something. When we enter this namespace in C++, you can observe that there's two ways in which you can render the namespace. You can either render it in this syntax where all the namespaces are concatenated into a single declaration, or you can render the namespaces namespace A, next line, namespace B. And so variability is what determines how to render. The namespace is the physical construct that we're trying to model, which we eventually were abstracted to the idea of a module. But the variability constraint defines the configuration options of that element. Then we enter the body of the file, and in the body of the file we define a single element, which is an enumeration, and so we have a type definition. So if you can imagine that if you apply this exercise to every single file that you see in a project, you will come up with lots and lots and lots of constructs. These are all physical constructs, and that's what we meant by when we're discussing here the physical domain. That's what we meant by the physical domain. So you can see this physical domain is quite distinct from a file because this physical domain has topology, which is different from how you normally visualize files because they tend to be flat. They're just a series of characters. That's not how we visualize a file artifact. Similarly, we did a similar exercise for folders. And in one perspective, one angle, you may think that folders are just, there's topology to folders because folders include folders. But our analysis went further than that. We tried to see what meaning a folder has in the context of a software project. And we defined one possible topology for those folders. Now, this topology does not, it's not a superset of all possible topologies. It's merely the MASD topology. It's the topology that we put forward that we think is sufficient for most use cases. That means that if you, as you are progressing in your usage of MASD, you will eventually converge towards this MASD topology, which may not be the topology you're used to. However, this is the supported topology. And the reason why we don't want to support every possible topology is because there's infinite amounts of folders structures that exist in projects. So instead, we put forward one topology. We enable you to configure it via variability, but it is the Mast topology. There is no other Mast topology. And that's one of the very important decisions we've taken from the beginning. We must constrain variability, so we can't allow you to do anything. It has to be constrained. And just double check how far we got. 50 minutes. So the proposed Mast topology effectively identifies the following folders with a given semantic. So there's the notion of a product, which is a top level folder. This will be equivalent to your Git folder in a repo. And then inside of that folder, we have a number of component collections. The collections basically, they have their own theme, I guess you'd call it. For instance, one component collection will be the components collection that contains all the source code folders. Another one could be a component collection with all the documentation, and so on. These are different kinds of folders that we got. Then we enter the components themselves. A component could be, for example, a set of files that make up a library or an executable. And then we tend to find, this again, this is a mass specific thing. We tend to find that a component could be projected across multiple technical spaces. So you could have a C++ representation of the component, you could have a C# representation. Now, you don't necessarily have that in most projects, but MASD does support that. Finally, within the components, we have this notion of parts. So an example of a part would be source or include in C++. These are distinct folders with distinct meanings. And you can have, for example, a public include directory and a private include directory. Those would be separate parts. And then you enter the world of facets, which is a Mast-specific concept. A facet is a grouping of the type definitions and other structural aspects that we have identified as part of our taxonomical work. So, for instance, we have identified type definition as one facet. We've identified text serialization as another facet, or more specifically, JSON serialization is another facet, XML serialization is another facet, and so on. And so, inside of MASD, we separate these structural features into their own facets. And finally, we now start to join in with the logical model, because modules, which are a logical concept, project themselves over to physical space as modules, as folders. And so you can imagine as part of the projection, now if I just go back to this representation, the projection of the logical concept of a module, which is our abstraction for namespace, package, and so on. As that gets projected to the physical model, it gets projected as a folder, but not just any folder. It's a folder that will exist as a component of a part. Of course, you may have facets elsewhere. So, for example, the component can have a facet. This is just basically how MASD decides to model it. And sorry, I was talking about modules. So modules can only exist as part of a facet. And so there you are. And this is an example in practice of the C++ product in MASD called C++ ref impl. And this is an example of all these elements in practice. So there are two component collections here. And the first one is build and contains a set of components related to the build. And the second set of components or component collection is projects, which is related to actual elements used with source code. So there are two components here, the boost model and the C++ model. The boost model is used to exercise functionality related to the C++ library boost. And the C++ model only exercises plain C++ functionality and STL, the standard library. Inside of the boost model, we have a series of parts. So in this case, we have a set of generated tests, we have includes, and we have source. And similarly, within the components for the C++ model, we also have these three elements. The components for the build are CMake, which contains a set of CMake files, and the output folder. So you see, this is just an instance of the morphology that we propose here. Okay, so I think we probably will end here, because the next thing we'll do is we will discuss the two case studies for Mast. So what we'd like to gather from this this presentation is from this lecture is the application of the Mast methodology to a set of projects was used as the basis for the analysis to create the taxonomy for Mast. And this is very important because we apply this process continually over time. And as we start to uncover patterns, and as we start to work on our library of SRPPs, as we discussed when we were talking about the mission, so the schematic and repetitive physical patterns, these patterns are the core of Mast. The identification of the patterns, the management of the life cycle of the patterns, that's the core of Mast. And so the work that we do in Mast is mainly a taxonomical and morphological work. We spend a lot of time thinking quite deeply about those patterns, and we try to put those patterns inside of a library. In fact, one thing we can do in this lecture, I'm just going to quit here for a second. I think a lot of these things are difficult to understand in the abstract. So perhaps if we just quickly show the cursor. What we'll do is very, very quickly, because we are reaching the end of our lecture. So if I just go up to our directory, I can't really see very well, but presumably somewhere around here we have Mast. So if I take Dogen, and if I look at a model in Dogen, so as you can see, all the stuff that we discussed up to now is represented in Dogen itself. There's the product. I mean, of course, we have multiple checkouts. So I have a checkout of the integration branch as well as the master branch. But you can imagine that this is the product folder for Dogen. And the component collection for projects is this one. And so inside of this component text, if you look at the models, you will find something really interesting. You'll find the technical spaces. If I go to the transforms, maybe if I make this a bit bigger so you can see. The technical spaces themselves are defined in here. And you can see this is defined as a technical space. And this is the definition of the technical space C++. And inside of that technical space, you then start to see the parts. So for example, the public headers, which is the includes directory. And inside there, you will start to see different components of that. What I really would like to show is the templates. So I would like to see the type definition if I could. Types, here we are. So here's the type definition for type definitions. This is a facet, as you'd expect from a physical perspective. And then in there, you start to see the different type definitions. There's quite a few of them. Of course, this is very, very difficult to wrap your head around because you must remember that we must define everything that MASD itself defines. So you will see type definitions for things like archetype. So that's just quite complicated. But if we just ignore those meta definitions and we look for something more practical, like a class header, you can see that the class header is defined here. And then inside of the definition of the class header, you would find the template. This template is used to generate class headers. And so for every single element that we classify, eventually there's going to be a template such as this one. And this template will then be used to instantiate those physical elements. I mean, I don't think I've got stitch mode enabled. Let's see. No, I don't. Let's have a quick look. I might be just here. If I just go up to the templating, there will be a list directory, and hopefully we can just load this guy. I think we have a problem with the version of Emacs that I'm using, I think. Oh, okay, right. So we don't have polymode installed. This Emacs is a bit dodgy at the moment. But if I had the mode installed, what you would see when you go to the template is you'd see this with syntax highlighting, and then you can start to see the structure of the template distinct from the structure of the code that we generate. So all of this to say what? The physical model elements that we discussed so far eventually get mapped into a model, which is this text model that contains all the definitions of those types. And for each of these, you'd have the pattern. The pattern is captured in the library, and this is the library, and this is the pattern itself. And the variability of the pattern is defined as things such as this, and so on, depending on whatever options you choose. So this should hopefully make it. I know it's a little bit confusing because you probably need quite a lot of time to get your head around a lot of the meta concepts inside of Dogen. But in a way, the meta concepts obscure what's being done here, which is actually quite a simple thing. All you're trying to do is you're trying to capture the patterns. You're trying to model those patterns as types. And when you created the model of those types, which we can probably see via a diagram. I probably shouldn't have opened this diagram because it's very large, and Emacs is not the best at rendering large SVGs. I think I probably will abandon that and just go to a browser, I think. So if I take, in fact, we already got a few here. So what you see here is a graphical representation of that model generated by Dogen. And you can see that the types are here, and you can see the definitions. So this is a structural representation of the types. And this is the logical model. Actually, this is the codec model. This is the logical model. And so when we spoke about the logical domain, these are the types in the logical domain. For example, model is one of those types. And this is a structural representation of model. And there's many other types, all in their separate namespaces. Templates themselves are also represented, and so is serialization, and so on. And these types then get projected over to the physical space, which will be here somewhere. And here you're going to start to see things like artifacts, which is a meta representation of a file. And we also have a model and so on. So that's how Dogen implements MASD. It is in effect a reflection of all the concepts that we described, all the meta concepts, I guess it would be fair to say, that we described so far. But in the next lecture, hopefully the final lecture, we will spend some time actually looking into the implementation of Dogen. I think it will be much easier to understand this concept when we look through the code. Okay, that's all for today. Thanks very much.